My name is Shafiq Qureshi. I'm on the games team. So I guess to talk about AI in games is appropriate. Let me just share my slides real quick and get this set up. Okay, this should be fine. Okay, cool. I kind of like the talk was originally mostly about generative AI in video games, but actually the way that I set up the talk was a little bit more about like AI in general in video games and then going into Gen AI in video games. So there's quite actually a bit of material in this setup, and I'm going to try to get through as much of it as possible. But what I'm going to quickly just go through is a few things here that are between just like starting at the history of AI in video games and going through the different levels of like how AI evolved in video games with basic algorithms like A star and D star, then going to decision-making processes, how early AI started to make decisions in video games on how to move characters and things like that, and then go into more of the general stuff. So I did a lot of demos for this. And some of it's in JavaScript, some of it's in Python, some of it's in Unity. So all of those are great for prototyping cool things with involving AI in video games, especially Unity, but the demos are kind of small scale, but let me get through it. So, so the first thing I'm just gonna do is kind of talk about the basics of like the history of AI in video games. So I think as most people know at this point that AI really started with Alan Turing back in the 30s and 40s when he was working on his fundamental computer science papers, and him and Alan Church were building lambda calculus, other kinds of fundamental things to basic computation, and things like the Turing machine and Turing test, et cetera, which he's well known for. And then most of what he did was then in his thought experiments applied to things like playing checkers and chess, which in itself is its pretty own interesting history. So then afterwards, the first games came out, the video games proper, like in 1958 and 1962. And that was games like Tennis for Two and Space War. Both of those, like Space War is interesting because it's in the Silver Ball arcade at the Asbury Park in New Jersey. So if you ever actually want to play it, it's been rebuilt. And you can actually play it. I do have a video of the Tennis for Two, but the point of that is the fundamental video game functionality was built so that AI could be integrated later. And then where AI really started to get integrated into video games was in the 70s, where you have the basic, most iconic video game of all, I think, is Pong, which has a pretty simple AI for just tracking the location of the ball. And this AI has no neural nets or nothing like that in there. It's pretty much just like if ball is traveling a certain direction, move the paddle the other direction. That's basically in the camp of what's known as symbolic AI. And it's just basically conditional logic. Space Invaders is similar. And then where AI algorithms really just started getting really involved as like algorithms that used intelligence as we know it was starting with in 1980 with Pac-Man. And Pac-Man it involved what we now term as finite state machine AI, which I'll go into later on, but it actually was the first like kind of learning system. And then moving forward a little bit, we start to get to the 80s where you have like games like Legend of Zelda. And Legend of Zelda is interesting because there's two kinds of AI which was involved. One was the basic like enemy AI, which is Link battling like Octoroks or whatever. And he's just like the enemy AI was pretty simplistic. But what was interesting about Zelda was that it was known for its more advanced NPC based AI, which made decisions based on how the game progressed and what quests you decided to do and which items you decided to collect. So this was actually pivotal in the way that AI was built for video games. And then I think where the modern age of AI in video games takes off is with Civilization back in 1991. And that was the first, what you call it, grand strategy game, where you had essentially different civilizations competing to be the primary civilization through trade, diplomacy, or war. And it was actually quite complicated. It wasn't a very simple system, and the symbolic logic rules were very involved. And then into more like action and other kinds of games where more tactical AI was involved was in 96 when Quake first came out. You started having the first AI that was able to react to players interacting in an environment and do things like hide behind obstacles and lure the player into traps and do much more complicated things than enemy characters in AI in video games were able to do beforehand. And then really, if anyone ever played Black and White was a game where you kind of raised like a character avatar, and it did a bunch of things, and you could train it to have like a moral compass and do some good things or bad things based on what you, the player, did. This was the first AI that involved things like decision trees and the ability to like learn from another system, learn from the player and its behavior, and then replicate its behavior. So also, just a precursor why I'm kind of going into the quick history of AI in video games is because like a popular conception in the modern day is that AI is limited to just more recent terms and it's something new, et cetera, et cetera. But there's been a lot of development from the world of video games into modern AI. And that's how a lot of more advanced systems actually became created because people invested in trying to solve like puzzles through games. So just I thought that might be an interesting tidbit and backstory as to how even the modern neural networks and things got like some of the capabilities that they did. So then really, I guess I could say into the 2000s, the advanced AI, if anyone has played Halo and has played, I guess, the Halo 2 really, a system that involved very complex coordination between enemy units was the main Halo AI, which, not to be confused with Cortana, but the behavior tree mechanic, which I'll also get into later, was integrated into Halo. And then it actually became much more complicated to actually defeat computers in like first-person shooter games. You actually had to spend a lot of time practicing to beat an AI when Halo came out. I will say that, and I'll make an exception for things like strategy games like StarCraft, but I'll get into that later. And then I think the first really like world NPC like source of slice of life AI came out with Elder Scrolls Oblivion. So Bethesda, who created the Fallout series, really went heads down into how to create a living world out of a video game where the characters that are not just the players but also the NPCs had the ability to live in the world and to like interact with the world and have their own lives and their own life cycles and death cycles, similar to how Sims started this, but it also advanced this beyond Sims significantly. So and the Radiant AI is still competitive with NPC like real world life AIs to this day. And then of course, the first AI that was able to beat a human was actually Deep Blue in chess in the 90s. I'm not skipping that, but like really the more advanced current day example is AlphaGo, which was developed by Google, DeepMind, and that was able to beat Lisa Dahl in 2017 at Go. Which was considered a remarkable advancement for AI in the ability to actually surpass a person. So that was years ago, actually, at this point. So interesting example. And then like finally, the last really big advancement, there's been many more smaller ones, but The Last of Us Part 2, the AI for that game, and it seems to be always the sequels that have more advanced AI, has what's currently state-of-the-art like benchmark beating enemy behavior, so to speak. So again, the ability for the enemy to actually behave like a tactical real-world opponent was involved in The Last of Us Zombies. So that's basically a quick history of like how AI in video games, kind of came together. I'm going to go over a few of the basic algorithms, but I'm going to go quick. I'm going to actually jump to the generative part because that's really the part that's really the most interesting stuff in the modern day. So the basic AI is based on pathfinding algorithms. That's how all the characters in AI kind of like do what they do. And the most well-known algorithm is known as the A-star algorithm. So if anyone has like gone, in your computer science classes, if you've taken like a computer science lecture, you've heard of Dijkstra's algorithm, or rather the shortest path algorithm, which predicts the shortest path between 2 points. The A-star algorithm is an advancement of that kind of figures out how to get from point A to point B intelligently as the character moves through space. So it knows the map, it computes the different points in the map, and then it figures out how to how to get to the end goal based on wherever it is on the entire map. And so any kind of obstacles in front of it, it can kind of negotiate these obstacles intelligently and learn from where it is. And that's what makes it AI based, because it's a learning mechanism. And it's pretty straightforward to compute this. It's just again like some conditional logic, but it was really like most systems use the A-star algorithm to some extent. But the A-star algorithm is good, but it relies on knowledge of the entire map. So in most real world scenarios, you don't know what your entire map is. So you have what's known as like the D-star algorithm. And so the D-star algorithm kind of figures out where you are on a map, and given incomplete knowledge, as you learn the map, as the character, as the enemy, and the enemy, just an enemy character, figures out more space around it and sees more like trees or like more hills or other things it can negotiate or obstacles, then it can dynamically update its understanding of the world to figure out how to negotiate these new algorithms. The standard A-star algorithm couldn't do this. So that's why in the so-called fog of war scenario, the D-star algorithm is primarily adopted to those situations. And so the next quick AI that I wanted to mention was the so-called nav mesh. And the navigation mesh, if anyone has actually built a video game, is the kind of the world that the AI can navigate. So it's kind of like an invisible structure on top of the different pieces of the world that as the AI traverses through, it can interact with and it can go over. And so I just have a video of how the nav mesh works here because I think that's more illustrative. So basically, if you have like, and so this is just basically me creating like, some kind of structure in Unity, and I'm importing that into another tool. And so this green area is the place where a character can walk over. And once the character knows it can walk over this plot, we can start off with like a fake character walking in the environment, which I have represented here. And this character then walks. We can start off the actual character walking. The character, now the nav mesh is now invisible, but the character knows that it can walk over certain navigable parts. And so like just speeding this along a little, the character can attack the player, which this is a simulated player character. This is not a particular game. This is just for testing purposes. But what's interesting is that the nav mesh allows you to create what's called destructible environments. So if you destroy like a certain part of your world, right, the navigation mesh can be structured in such a way that the enemy knows that it can walk over a part of that mesh, but then there might be another part of the mesh that's a one-way mesh. So the whole point of showing that, and so the enemy couldn't traverse there over that location. So the whole point of showing that is that like you can simulate very complex enemy behavior just by creating the structure of the world that the enemy understands. So something like a navigation mesh. So let me exit out of that. So I'm just going to quickly go over decision-making algorithms and then get into actually the details of like how generative AI works, because this is a bit of a shorter talk than initially planned. But so the basic decision-making algorithms in AI are known as like finite state machines. And FSMs are in computer science's basic like conditional logic system that if a character is in state A or if the system is in state B or A, then it can transition to another state if given a condition is met. So it's basically if then else, but it puts the entire system or the game or whatever in a particular state. So whether, for example, if a door is open, then the door can be closed. And if the door is closed, then the door can be locked. If the door is locked, then it can be unlocked. And these are all states of the door/person system. So again, as I mentioned, Pac-Man was the first game that really involved the idea of the finite state machine, the FSM, where you have the several different kinds of ghosts that do things based on whether what color the ghost is. So if it's red, it behaves in a certain way, blue in a certain way. If Pac-Man eats one of the pills, all the ghosts behave differently and try to escape Pac-Man until the pill wears off. And so then these are all just simple states. But if you think about it, this simple system is artificially intelligent because these ghosts are actually kind of like learning. There's basic rules, but they're learning how to attack Pac-Man based on their state. So something just to keep in mind on the concept of symbolic logic. And then we have something on the idea of behavior trees. So the idea of a behavior tree is where you have a series of actions that agent can take. And I'm just going to call them agents now because these are all essentially what agentic behavior in the modern parlance like computes to. So if there's a series of actions that some character can take based on the action that it's taking or the state that it's in, there can be a whole different sequence of sub-actions that it takes. And as I mentioned before, Halo was really one of the games that really made behavior tree mechanics very powerful. So systems were able to navigate like through complex worlds with complex enemy interactions with the player through the idea of like complex behavior trees. And what you see on the right is essentially a behavior tree builder in Unity. So you can create a behavior tree, and then based on certain conditions, you can see what the enemy is thinking. So this highlighted path is deciding what to do based on like what the player is doing. And so as you can see, this is essentially what what thinking is in the computer. You can visualize it. And then if you ever played Minecraft, so that was behavior trees. Then the next biggest category that I'm going to talk about in behavioral mechanics is the so-called hierarchical task network. So if AI has to do something and plan out a behavior, a more complex plan than just reacting to tactically to like an input from a character and a player. Then, like for example, if in Minecraft, if your player has to build out a house, then it has to break down the entire process of building the house out into several subtasks. How these tasks are built out are based on the concept and the theory of goal networks and task networks. And so the AI takes a complex task, breaks it down, and then is able to accomplish everything by doing the smaller tasks. So this is almost like just a breakdown of it, how it looks. And all of these structures are like basically tree-like structures, as you can tell. So this is basically the tree. And this is essentially like, for example, like if a boat is capsized, if you need to rescue people, the essential AI doing this would have to go through these smaller tasks before it could actually accomplish this larger task. And so I'm not going to go through all of this here because this is concept of dynamic difficulty adjustment. And this is another behavioral thing, but it's also based on like certain games where the difficulty of the game actually has to get more complex as the player advances through the game. So if you start out easy, the enemies are, you start out like as a new player and the enemies are easy, but as you advance, the enemies become more challenging because they use a combination of the previous things like behavior trees and finite state machines and other systems to adjust the difficulty of the game to get more complex. And what's interesting is that so I built just a quick like demo of a game that I did where this is I built in JavaScript. So basically you're a player, you're trying to attack like enemy blobs or whatnot, and they're moving away from you. One is shooting at you. And then as you attack enough of them, what happens is they become more powerful and they start shooting faster. And so it becomes harder to actually beat the game because I have this difficulty meter on the side, which you can't really see, but it increases, meaning the speed of the shooting thing increases as you go through and like kill more enemies. So finally, that's essentially a basic dynamic difficulty adjustment system. And there's a lot that we can get into in that, but I'm going to just move straight over to generative AI in video games because that's like the super interesting thing in these last few minutes. So the first thing is the idea of like procedural content generation. So essentially procedural content generation is like where everything kind of really started with like generation in games, where you have the idea of if you've seen the Game of Life, Conway's Game of Life, you have these basically cellular automata-based systems that create new things based on the state of the system. So as you can see, the system started at a very simple, pixel, 2 pixels next to each other. Then the logic of the system causes this kind of emergent behavior to create all these new behaviors. So this is actually, you can code this up pretty simply with a few lines of code, and it can actually create very complex emergent worlds from just this basic idea. So then again, not going too much into the way that graph grammars work, but graph grammar is like another system which creates, you take the Game of Life cellular automata idea, and then you use what's essentially the concept of a computational graph. And then just giving you the visual here, you can kind of create whole new worlds and generate whole new systems from this. So basically all these edges kind of spawn based on rules that if one edge spawns another edge, then a new edge appears, and then another edge appears based on the spawning of that old edge. And thus you can get a very complex graph just from a basic, simple rewriting rule, as it's called. So a lot of games in general create their procedural worlds based on that and generate procedural worlds based on the concept of the graph grammar. So it's very interesting to look at, and you can actually simulate that very simply. I do also have a graph grammar simulation, but it would take a little while to go over the details. But I basically have this simple city plan. And it's just, again, a city with blocks that are like on the top view of the city, that I can generate whole new cities just by simply changing the graph grammar rules. So I have that simple grammar that I wrote, and then essentially the entire city becomes like this different, complete, bustling metropolis. And depending on the complexity of the grammar, you can, and this is all in JavaScript, by the way, you can create much more complex environments that are not just simple cities, but like more complex things, like something that has like the downtown, like FiDi kind of neighborhood mixed with a metropolitan neighborhood, something that's not just like rectangular blocks of city plan. So that's very interesting. And this is also just using like a graph grammar based system to create. So now into the modern day, graph grammars have been around for a while, but then you have in the modern day the concept of super resolution in video games. So basically as character, like when you had to create a 3D character in a video game prior, you essentially had to use a lot of 3D editing and a lot of 3D modeling, and you had to get a modeler who could build out a character, and it would take some special expertise in Unity and Blender, etc. Now these days what people are doing is called super resolution upscaling. So what they do is that they take like a low poly character, and then they'll apply like a super resolution filter, usually called something like ESR or GAN, generative adversarial network, and then they will create like a realistic, real-time representation of that low poly character. And this is becoming more and more popular in games to save resources because it's much, much more faster than rendering an entire like 3D mesh. So you'll be seeing, this is already there, and you'll be seeing more of this kind of super resolution upscaling happening in games as time goes on. So moving over to LLMs, because that's what I think everybody's like super familiar with at this point, is the concept of LLM-based games. So there's a really popular LLM-based game out there called Infinite Craft, and I don't know how many people have played it, but it's basically a game where you can combine things together, like random objects together, and you can create whole new objects out of them. So you have this like these basic objects, and as you create new objects by like moving blocks on top of blocks, whole new things appear. And what's interesting is there's tons of videos out there how people created these whole new objects from scratch based on an LLM, evaluating what the two combinations should be and creating a whole new output. And every time a whole new output is saved, it's like you're known as the discoverer of this output. So people will spend like tons of time becoming discoverers and creating whole new discoveries based on the LLM that's writing Infinite Craft under the hood. It's a pretty addicting game if you're interested in ever playing it. So then, again, the final thing in the LLM-based game category, because I'm getting close to the end, is basically how NVIDIA has combined with, I'm going to play this loud, has combined with several companies, but Convey is one of them, to create like a system that allows for...
Our latest collaboration is with Convey, a developer platform that enables easy integration of Gen AI-powered game characters. Convey's platform features a set of tools and APIs to create character personas and enable dynamic conversations leveraging the new NVIDIA Audio-to-Face and Riva microservices. Let's take a look. In this demo, we're back in the ramen shop with Jin, except this time, we're joined by Nova, a cybersecurity expert in our cyberpunk-flavored world. Let's listen in as these two AI game characters have a generated conversation.
Nova, you ever get that uncanny feeling we're like those AI constructs from the old sci-fi flicks? But nah, we're too quirky for that.
The cool thing is, the conversation's different every time.
Quirky is one word for it, Jin. I think we're just too real to be anything but flesh and blood. You're not wrong, Jin. Sometimes I wonder if we're all just part of some elaborate cybernetic dream. If we were AIs, I'd be the one cracking jokes about the singularity over a bowl of ramen. Kai, long time no see. You've been hiding in the shadows, or have you just been trying to avoid me?
Hey, Nova, it's good to see you. I haven't been trying to avoid you, just been super busy. How are things?
Things are fantastic. Just secured a juicy contract with Zenith and Sons.
Okay, so you get the idea. Is that I'm close to the end of the presentation time, but the idea is like real-time interactions are being built with LLMs in games right now, and the ability to actually respond to them like with real live voice recognition on the moment is also available and right now built into the game system. So there's actually quite a bit more that I could get into, but I'm kind of out of time. But I just wanted to say that there's like a lot, in AI and video games. And the last thing I'll just play a video of is the first video game that actually was considered out there as candidate for two. And so this was, I believe, built on a PG-11 back in 1958, which was 18 at this point. It had like 100 bytes or something, or like 200 bytes, and it's basically a game controller built at MIT. It's nothing like the keypads you see today, but just virtually everything sounds good. So yeah, that's basically my presentation.